You know that sharp, sour taste of a lemon? Or how baking soda feels kind of soapy and tastes a bit bitter? Well, ever wondered why? It's all about these invisible chemical players, acids and bases. And believe me, they are everywhere, in our food, our soaps, even inside us.
We've all been there, right? That horrible feeling of acidity after a big, spicy meal? Or that moment of panic when you see a bright haldi stain on your favorite white kurta. You might think these are totally different problems, but guess what? They're actually little chemical mysteries, and today we're going to solve them.
So what's the secret? Well, the solution to both these problems. It all comes down to this epic, fundamental battle, acids versus bases. Seriously, understanding how these two interact is the key. It's like this constant balancing act happening all around us and even inside us. So come on, let's get into it.
All right, so here's our game plan. First, we'll find these acids and bases hiding in plain sight right in our homes. Then we'll play detective and figure out how to spot them. We'll see what happens when they react, uncover their secret superpower, learn how to measure just how strong they are, and finally, wrap it all up by seeing why any of this is so important in our day-to-day lives.
Okay, first things first. When you hear acids and bases, you probably picture a science lab, right? With people in white coats and bubbling beakers. Well, let's get that idea out of our heads. These things aren't just in labs. They're the invisible ingredients of our actual life.
Just think about your own kitchen for a second. That sour taste in nimbu pani, that's citric acid. The sharp tang and vinegar you use for noodles, acetic acid. Even the khatta taste in imli chutney comes from something called tartaric acid. And then you have the other team, the bases. They're usually a bit bitter and feel soapy. Think about baking soda or just a regular bar of soap.
Okay, so we've established that tasting everything is a terrible, terrible idea to figure out what's an acid and what's a base. So how do we do it then? Well, for that, we need our very own chemical detective kit.
And the number one tool in this kit is something called an indicator. It's basically a chemical spy that changes color to tell us if it's hanging out with an acid or a base. It's like a little magic trick, and you don't even need a lab. Nature gives us some amazing ones, like litmus or even haldi from our own masala box. Think of each indicator as having its own secret code. It's a language of colors. For instance, if you dip blue litmus paper into an acid, poof, it turns red. And then there's this one called phenolphthalein. It's totally colorless, but the moment it touches a base, it turns this beautiful bright pink.
But wait, what if you can't see the color? Does the detective work stop? No way! Chemistry has another cool trick, and this one uses your nose. They're called olfactory indicators. These guys change their smell. Take an onion, for example. A base will completely kill its strong smell, but an acid won't touch it. How cool is that? You can literally sniff out the difference.
All right, we know how to find them and how to identify them, but what happens when these acids and bases actually, do something? What happens when they react with other stuff? Well, this is where things get really interesting.
So let's look at a classic showdown, an acid versus a metal. When they get together, the metal basically kicks the hydrogen out of the acid and takes its place. What you're left with is hydrogen gas and something called a salt. Now, don't just think of table salt. In chemistry, salt is just the name for the compound that's made in this kind of reaction. It's a really classic example of just how reactive acids are.
And here's a perfect picture of that in action. You see those little pieces of zinc metal being dropped into the acid? All those bubbles fizzing up? That's not just air. That's hydrogen gas being born right there in that test tube.
But how can we be sure it's hydrogen? Oh, there's a super famous and fun test for this. If you manage to catch that gas and bring a flame near it, you get this amazing little pop sound. That pop is like hydrogen's signature sound, telling you, yep, it's me.
Okay, so acids react with metals. But what happens when an acid meets its total opposite, a base? Well, they do something called neutralization. It's like they're perfectly matched opponents that just cancel each other out. And what are you left with? Just simple salt and water. Remember that acidity problem we talked about? This is exactly how an antacid tablet works. It's a base that neutralizes the extra acid in your stomach. See? Chemistry for the win.
So, we've seen what acids and bases do, but the bigger question is, why? What is their secret? What gives them these superpowers to react the way they do? For that, we need to zoom way in, down to the molecular level, and talk about these things called ions.
Check out this experiment. You've got a simple circuit with a battery and a bulb, but there's a gap, so the bulb is off. Now, if you fill that gap with pure water, nothing really happens. But The moment you add some acid to that water, the bulb lights up. So, what's going on? The acid releases these tiny charged particles, called ions, into the water. These ions are free to swim around, and they carry the electricity across the gap, completing the circuit. It's these ions that do all the work.
So, that's the big secret. When you dissolve an acid in water, it releases hydrogen ions. We call them H+ ions. And when you dissolve a base, it releases hydroxide ions, or OH- ions. These free-floating, charged little things, they are the real source of the power. They're the ones causing all the reactions we've been talking about.
Okay, so it's not like all acids are the same, right? Some are super strong and dangerous, and others are so mild you can have them in your food. So how do we tell the difference? We need a ruler, a way to measure their strength, and that's where the pH scale comes into the picture.
The pH scale is basically a scale from 0 to 14. Right in the middle at 7 is neutral. Think of pure water. Anything below 7 is an acid, and the lower the number, the stronger it is. So a pH of 1 is a really, really strong acid, and anything above 7 is a base, or alkaline, with 14 being the strongest base.
And this chart really helps put things in perspective. You can see lemon juice way down there with a pH of around 2.2. That's pretty acidic. Then you've got pure water chilling in the middle at a perfect 7. And way over on the other end, you have something super basic like sodium hydroxide, which is all the way up at 14. Big difference, right?
Okay, so we've gone through all this chemistry, indicators, ions, pH scales, but you might be thinking, so what? Why does this actually matter to me? Well, let's connect all the dots and see just how much pH runs our daily lives. Think about this. Your stomach is literally filled with strong acid to digest your food, and antacids, just bases to calm it down. Your teeth start to decay when the pH in your mouth drops below 5.5, so your toothpaste is basic to fight that. Got a bee sting? That's acid. So what helps? A mild base like baking soda. See? It is literally everywhere.
And this quote just says it all, doesn't it? The same basic rules of chemistry that explain why you get acidity are also at play on a whole other planet, creating clouds of sulfuric acid on Venus. It's not just about our kitchen or our body, it's universal.
So now you're in on the secret. The next time you use vinegar to clean something, or put baking soda on a bee sting, or even see a farmer checking their soil, you'll know exactly what's going on. You'll see that invisible chemical battle playing out. So you've got the basics now. The real question is, what other everyday mysteries are you going to solve with this knowledge?